All right, welcome back. So today we're going to be looking at something called standard reduction potentials and using this to calculate the cell potential, or in other words, just how much voltage an electrochemical cell can produce depending on the identities of our two half cells. So just some terminology out of the way. If you hear something called oxidation potentials, this is just the ability of a half cell to lose electrons, because oxidation is a loss of electrons, whereas reduction potentials is the ability of a half cell to gain electrons. Now, that word reduction potential you probably have already seen before. If you switch to your data booklet and look up here, we got a table of selected electric potentials, and we have our reduction half reactions right here, and we have the electric potential. So kind of what we have right here is a table of reduction potentials. So these potentials are measured using a voltmeter, of course. So each reaction listed in data booklet has a cell potential measured with it. It is assigned in volts. Now, reduction half reactions have a positive electric potential. They have a greater tendency to gain electrons and are stronger oxidizing agents. So that is also why when you look at your data booklet, fluorine has the highest positive reduction potential. Now, it is impossible to just measure a voltage of just a half cell, because in order to have a fully functioning cell, same thing with a battery, you need to have electrons flowing, you need to have a positive terminal and a negative terminal. So in our data booklet, all of these values are with respect to one common cell. And it is the one here labeled as 0, 0, and that is the hydrogen half cell. And that's why the hydrogen half cell is kind of right in the middle of a data booklet as well. So we kind of have like all these are stronger reducing agents, and of course we have or stronger reduction potential, and of course the lower reduction potential down here at the bottom. Now, it's kind of arbitrarily chosen. It is just a reference cell that was created. It doesn't need to be there. It's just this is what they're all assigned to for this particular data booklet. Now, all the values are arbitrarily assigned on a standard cell. So the hydrogen half cell was designed as this one for our own data booklets, and that is why it has 0.00 volts. So depending on what is your standard cell is always going to have 0.00 volts. And just for our data booklet, we have hydrogen. If it's another set of values with another half cell, then they're going to have completely different values. But as we said back in our last lesson, the voltage a battery is going to put out is dependent on the identity of the substances used. So in order to predict the voltage of a voltaic cell, we have this right here. So this right here, so this is the potential of the cell. So delta E naught net, this is the potential of the cell. We take the reduction potential of the cathode and we minus the reduction potential of our anode. So all we need to know is which one is our cathode and our anode, and we can figure it out. So for example, calculate the cell potential, E naught of the standard nickel copper cell. So remembered, for a standard cell, we have both the solid and we have the ion. So basically we have these are all of our entities present. When we have that, and we know we're separated there as well, but it doesn't really matter. We don't really need to separate it or show it. So between nickel and copper, we see copper up here. Our copper 2 ion is our strongest oxidizing agent, and our nickels are down here, and nickel solid is our strongest reducing agent, right? So when we are trying to figure out which is our anode and what is our cathode, we are going to label these here. So we know copper 2 plus was our strongest oxidizing agent, and we know strongest oxidizing agent is reduced, and reduction happens at the cathode, where our strongest reducing agent is always oxidized, and oxidation happens at the anode. So that is why when we take our values, we take our cathode and we minus the value of our anode, and we do not change the signs as well. So, and we know our cathode is copper 2, so we go back to our data booklet, we find copper, which was up here. It has a cell potential of positive 0.34, and our nickel was a negative 0.26. All right, so we put in these values that are there. So we have a positive 0.34 volts minus a negative 0.76 volts, and we are left with sorry, I used the wrong values there. Just let me go back and change that. As a positive 0.34 and negative, because it's nickel. Sorry, I was looking at zinc for a second. That's the next one. It's negative 0.26 volts, and we get a positive 0.60 volts. So that is how we use our data booklets, and of course the whole idea of oxidizing agent and reducing agent. Now similarly, when we get to our next one as well, like calculate the cell potential reaction between zinc and copper 2 sulfate. Now this is no difference on how you solve these here. You're still going to write out all the entities in solution, right? So we got zinc solid, we got copper 2, we got sulfate, and we got water present because of the aqueous. Now of course when we go through here, you're going to use your data booklet and find out that zinc solid is our strongest reducing agent, so that's going to put this at the anode. I don't know why I wrote 2 A's there, sorry, just let me fix that. Because strongest reducing agent is oxidized, oxidation happens at our anode. And then we are going to find copper 2 plus is our strongest reducing agent. Strongest reducing agent is always oxidized. Strongest oxidizing agent. God, getting myself confused here. Copper 2 plus is your strongest oxidizing agent. Sorry. Strongest oxidizing agent is always reduced. Reduction happens at the cathode. So if we want to find the cell, we take the potential of our cathode, we minus the potential of our anode. You reference your data booklet, you find our cathode is copper 2 plus. We just used it in our example up above, which was 0.34 volts, minus the cell potential of zinc this time. You can reference your data booklet, but you will find it's a negative 0.76 volts, and we get a cell potential of a positive 1.10 volts. All right, now, so for the next one here, and this is very typical of what you normally see if you were going to do the diploma exam for chemistry, is that sometimes they like to take it as we know that hydrogen half cell is our standard half cell. So this is a series of questions like, what if we change our half cell? In this case right here, the standard silver half cell is used as a reference instead of the hydrogen half cell. So therefore we have to get new cell potentials, basically creating a new chart over here. Because like I said, hydrogen is our half cell, so that's why it's at 0.00. But if we were to get a new half cell, like silver, being this right here, that means that if this was going to be a half cell, we're going to have to convert the 0.80 down to 0.00 volts. Well, how do we do that? Well, what we take is just we subtract, well, the cell potential of this. And to get our new numbers for everything else, we're going to have to do the exact same subtraction. So that is what we're going to do here. So if we're asked what is the new reduction potential of the nickel half cell, so the reduction potential new is going to equal the reduction potential of the old minus the cell potential of our new standard. So there's no real formula for this. I'm just kind of showing you on how to actually do it. I don't know why I said new. Now for our nickel, its old reduction potential was negative 0.26 volts. Our silver was 0.80 volts. So our new reduction potential is a negative 1.06 volts. We can do the exact same thing for our copper as well. So the new reduction potential for copper, same thing, well, for our new reduction potential new is equal to the reduction potential of our old minus our new standard. And for copper, the old reduction potential was a positive 0.34 volts. Same thing, silver is our new standard, so we're going to subtract 0.80 volts, and we're left with negative 0.46 volts. That is it. So we are going to use two of these to now calculate the cell potential. And this is, you're going to see that because we're just standard nickel half cell, standard copper, the next question is going to ask what is the cell potential between nickel and copper, both standard, right? The net electric potential for this voltaic cell. Remember, we have nickel, the standard nickel half cell, so that means we have nickel 2 plus nickel solid, and we got copper solid and copper 2 plus. Now when you go to your data booklets, you're going to find nickel solid is your strongest reducing agent. Strongest reducing agent is oxidized. Oxidation happens at our anode. And you're going to find copper 2 plus is our strongest oxidizing agent. Strongest oxidizing agent is always reduced. Reduction happens at the cathode. So, go our cell. We take potential of our cathode minus that of our anode. And we're going to take the values on the previous page. So our cathode, as we have right here, was copper. And on our previous page, copper was a negative 0.46 volts. And we subtract our nickel on the previous page, 0.6 volts, and we get positive 0.60 volts. Now compare this answer from C with the answer in example 1. So answer in example 1, if we go back, was the same thing, calculate the potential difference between nickel and copper, and we got a positive 0.60 volts. Now we change the standard and we get the exact same answer. The reason for that, voltage is dependent on what materials are used. And that is why, so that goes back to what we did yesterday when I talked about voltage. The only thing that matters for voltage is what materials are actually used. So that means if you set up a standard, or if you set up a cell that has both nickel and copper, you're going to produce 0.6 volts. It doesn't matter what the reference is to compare a half cell. All that matters is when we connect them, the entire cell is going to produce 0.6 volts. Now, normally we do a lab with these here as well, but obviously we don't have that ability right now where we have different electrodes and electrolytes and we get to play with them and see if we get close to the potential or not. And a lot of the times you don't. And the reason for this, there's a bunch of different reasons. Of course, we always assume standard concentration, so 1 mole per liter, 25 degrees Celsius, and pressure is 101.325 kPa. That's what we assume. Now, obviously, that's not always the case, just because concentration, I think in our lab that I was going to get you guys to do, it was a 0.1 mole per liter solution, just because to make a 1 mole per liter solution costs a lot of money to dissolve all of those compounds in there, so I kind of dilute it a little bit. Now, of course, non-standard conditions is the major reason why these you don't get the same expected potential, but also the purity of substances that happens. You get impure substances, you get conflicting reactions. If you get anything where your anode or your cathode is reacting but not the way it needs to, that's because of purity. You can get coatings on the metals, so oxide coatings, and then of course even the type or the size of porous boundary. Now normally the salt bridge is the best, but if you're using a porous cup, if the pores aren't big enough to let the anions and the cations through, you're not going to get a transfer of ions, therefore you're not going to have a completed cell. And that also has an effect on the voltage that is there. So that is it for our calculating our standard potentials and everything like that. You have definitely a lot of work in your booklets to kind of keep going through. I can't remember. Oh, there is a few diploma examples right here where we have some unknown cells. Now, ideally, you should probably just have a look at these here and try to answer them. So you can pause it and just go, and I'll go through the answers here now in 3 seconds. All right, and of course, for this one right here, when we read 18, the half reaction occurs at the cathode. So now cathode is reduction, and this is your strongest oxidizing agent. Now, we have two reactions right here. In order to tell which one's our strongest oxidizing agent, we have to look at our cell potentials. And we also have to kind of reference our data book. We'll notice our strongest oxidizing agent has the highest positive electric potential or reduction potential. So you kind of need to clue into that and know that the way this table is organized, this right here, this is actually my strongest oxidizing agent, or this right here is my SOA, and that's going to be reduced. So therefore, the reaction occurs at the cathode is going to be that one right here. Understanding that the one with the highest reduction potential is the one that's going to be reduced, therefore is the strongest oxidizing agent, and that is the reaction that is going to occur at our cathode. So then for part B, or sorry, for 19 here, the reference cell was changed from standard hydrogen half cell to standard cadmium half cell. Then the reduction potential for equation 1 would be, well, this goes back to kind of what we did last time, is that equation 1 we have right here. So we're going to take the old minus our standard. So we take our positive 0.58 volts and we minus the reduction potential for cadmium. So we just have to go to our data booklet and we have to try to find cadmium. And cadmium is all the way down here of a negative 0.40 volts. So we just put that in, minus a negative 0.40 volts. And we should be left with, at this point right here, a positive 0.98 volts, which makes that answer D. So that is it for these here. So please go through your workbooks, try to work on these as much as you can. And of course, next lesson, we're going to be looking at what happens if a cell is not spontaneous, and that is what we call our electrolytic cells. So see you guys for the next one.